An electric car is powered by an electric motor instead of a gasoline engine. The electric motor gets energy from a controller which regulates the amount of power based on the driver's use of an accelerator pedal. The electric car, also known as an electric vehicle or EV, uses energy stored in its rechargeable batteries, which are recharged by common household electricity. How it works? Well, the gasoline engine is replaced by an electric motor. The electric motor gets its power from a controller. The controller gets its power from an array of rechargeable batteries. To make an electric car, the gasoline engine, along with the muffler, the catalytic converter, tailpipe, and gas tank are all removed. The clutch assembly is removed. The existing manual transmission is left in place and is pinned in second gear. A new AC electric motor is bolted to the transmission with an adapter plate, and an electric controller is added to control the AC motor. The controller takes power from the batteries and delivers it to the motor. The accelerator pedal hooks to a pair of potentiometers or variable resistors, and these potentiometers provide the signal that tells the controller how much power it is supposed to deliver. The controller can deliver zero power when the car is stopped, full power when the driver floors the accelerator pedal, or any power level in between. The controller normally dominates the scene when you open up the hood, as you can see here. It is labeled US Electric Car. When you push on the gas pedal, a cable from the pedal connects to these two potentiometers. The potentiometers hook to the gas pedal and send a signal to the controller. The signal from the potentiometers tells the controller how much power to deliver to the electric car's motor. There are two potentiometers for safety's sake. The controller reads both potentiometers and makes sure that their signals are equal. If they are not, the controller does not operate. This arrangement guards against a situation where a potentiometer fails in a full-on position. In this picture, heavy cables on the left connect the battery pack to the controller. In the middle is a very large on and off switch. The bundle of small wires on the right carries signals from the thermometers located between the batteries, as well as power for fans that keep the batteries cool and ventilated. This is a picture of heavy wires entering and leaving the controller. The controller's job in a DC electric car is pretty easy to understand. The controller reads the setting of the accelerator pedal from the potentiometers and regulates the power accordingly. Let's say that you have the accelerator pushed halfway down. The controller reads that setting from the potentiometer and rapidly switches the power to the motor on and off so that it is on half the time and off half the time. If you have the accelerator pedal 25% of the way down, the controller pulses the power so it is on 25% of the time and off 75% of the time. In an AC controller, the job is a little bit more complicated, but it's basically the same idea. The controller creates 3 waves. It does this by taking the DC voltage from the batteries and pulsing it on and off. In an AC controller, there is the additional need to reverse the polarity of the voltage 60 times a second. Therefore, you actually need 6 sets of transistors in an AC controller, while you need only 1 in a DC controller. In the AC controller, for each phase, you need 1 set of transistors to push the voltage and another set to reverse the polarity. You replicate that 3 times for the 3 phases, 6 total sets of transistors. Electric cars can use AC or DC motors. If the motor is a DC motor, then it may run on anything from 96 to 192 volts. Many of the DC controllers used in electric cars come from the electric forklift industry. If it is an AC motor, then it probably is a 3-phase AC motor running at 240 volts AC with a 300-volt battery pack. The charging system of an electric car has 2 goals: to pump electricity into the batteries as quickly as the batteries will allow, and to monitor the batteries and avoid damaging them during the charging process. One system accepts 120 volt or 240 volt power from a normal electric outlet. This kind of system, the normal household charging system, has the advantage of convenience. Anywhere you can find an outlet you can recharge. The disadvantage is charging time. A normal household 120 volt outlet typically has a 15 amp circuit breaker, meaning that the maximum amount of energy that a car can consume is approximately 1,500 watts. Since the battery pack in this car normally needs 12 to 15 kilowatt hours for a full recharge, it can take 10 to 12 hours to fully charge the vehicle using this technique. By using a 240 volt circuit, such as the outlet for an electric dryer, the car might be able to receive 240 volts at 30 amps. This arrangement allows significantly faster charging and can fully recharge the battery pack in 4 to 5 hours. This picture is a picture of the estimated yearly cost of running the Chevy Volt compared to other electronics. As you can see, it's the fourth plug down with $292 per year. Now that's pretty close and a little bit less than air conditioning, refrigerator, water heater, the things you use every year, and it's just about the same cost. Another type of charging system is the MagnaCharge system, which consists of two parts: a charging station mounted to the wall of the house, and a charging system in the trunk of a car. The charging station is hardwired to a 240 volt 40 amp circuit throughout the house's circuit panel. The charging system sends electricity to the car using the inductive paddle. The paddle fits into a slot hidden behind the license plate of the car. The paddle acts as one half of a transformer. The other half is inside the car, positioned around the slot behind the license plate. When you insert the paddle, it forms a complete transformer with the slot, and power transfers into the car. One advantage of the inductive system is that there are no exposed electrical contacts. You can touch the paddle or drop the paddle into a puddle of water and there is no hazard. The other advantage is the ability to pump a significant amount of current into the car very quickly because the charging station is hardwired to a dedicated 240 volt circuit. As far as the impact on the environment goes, electric cars create less pollution than gasoline-powered cars, so they are an environmentally friendly alternative to gasoline-powered vehicles, especially in cities. The vehicles are powered by fuel cells, so that helps. The problem with electric car production is right now the weak link in any electric car is the battery. There are at least 6 significant problems with the current lead-acid battery technology. They are heavy, they're bulky, they have limited capacity, they are slow to charge, they have a short life, and they are expensive. You can replace lead-acid batteries with nickel metal hydrate batteries. The range of the car will double and the batteries will last you 10 years. But the cost of the batteries today is 10 to 15 times greater than lead-acid. In other words, nickel metal hydrate battery pack will cost $20,000 to $30,000 today instead of $2,000. Prices for advanced batteries fall as they become mainstream, so over the next several years it is likely that nickel metal hydrate and lithium-ion battery packs will become competitive with lead-acid battery prices. Electric cars will have significantly better range at that point. Just about any electric car has another battery on board. This is the normal 12-volt lead-acid battery that every car has. The 12-volt battery provides power for accessories, things like headlights, radios, fans, computers, airbags, wipers, etc. Since all of these devices are readily available and standardized at 12 volts, it makes sense from an economic standpoint for an electric car to use them. Therefore, an electric car has a normal 12-volt lead-acid battery to power all of the accessories. To keep the battery charged, an electric car needs a DC to DC converter. This converter takes in the DC power from the main battery array and converts it down to 12 volts to recharge the accessory battery. When the car is on, the accessory gets their power from the DC to DC converter. When the car is off, they get their power from the 12-volt battery, as in any gasoline-powered vehicle. Other problems during development are that a number of entrepreneurs who are not content in following the slow timelines from the major car companies, have taken the bold step of building mainstream highways capable of all-electric vehicles. The payoff could be big. Things like federal highway crash testing are daunting and very expensive. Those costs will get passed on to customers, those that are willing to wait for months or years for innovative companies to roll out models even in small quantities. The poster child of the independent electric car movement has been Tesla Motors. When the company launched, it promised to reinvent the auto industry in the mold of a Silicon Valley startup. After hitting a number of potholes, product delays, and major operating losses, the company emerged looking good, with momentum for the electric car startup. In the picture shown is the Tesla Roadster, a screaming fast, all-electric two-seater sports car. The specs, if they can be delivered, are impressive. 0 to 60 miles per hour in less than 4 seconds, 135 mpg equivalent, 200-mile range, and a brilliant tech design that wires together nearly 7,000 mass commodity rechargeable lithium batteries. The price is just north of $100,000. The 2010 Tesla Roadster continues to earn praise for its acceleration. What Scientific America calls an insane amusement park ride, the company has delivered nearly 1,000 Roadsters as of November 2009. Shown in this picture is the Tesla Model S. What makes the Model S so cool? First of all, the visual design is gorgeous. Second, it seats 5 or 7 if you count the 2 side-facing rear seats for small children. There are killer features like the 17-inch touchscreen that provides all of the vehicle's interface components such as climate control and entertainment, but also offers 3G or wireless connectivity. But most importantly, the Model S is way more affordable than the company's $109,000 Tesla Roadster. The current price target for Tesla Model S is $57,900. The Model S is planned to release in late 2011. BMW is working on a small electric car that could launch in 2012, the Megacity. It's a low-slung 3-door, 4-seat hatchback coupe. The car is smaller than the Honda Fit and will have a projected range of 100 miles. The BMW Megacity is not much more than a concept at this stage, but pressure on BMW to meet California's zero-emissions vehicle requirements might bring the car to life. Shown in this picture is the Coda, or the electric sedan. Southern California automaker Coda Automotives announced plans to bring a new electric car to the U.S. from China in 2010. Re-engineered with a lithium-ion battery, the Coda sedan promises a driving range of 100 miles. The MSRP for the Coda sedan will be around $40,000. The scrappy California company may be the first startup to offer a practical and affordable electric car to mainstream buyers. Nissan is calling its new electric car, the Nissan Leaf, the world's first affordable zero-emissions car. And they could be right. Unveiled on August 2, 2009, the Leaf is a medium-sized all-electric hatchback that seats 5 adults and has a range of 100 miles. Pricing was not announced, although the company previously hinted at a price around $30,000. The Nissan Leaf's closest comparable future all-electric car is the Ford Focus EV. The distinguishing characteristics between the two vehicles could be design, pitting the established look of the Ford Focus against the purpose-built Nissan Leaf, which will go on sale in late 2010. The Ford Focus EV, due out in late 2011, is the first electric car designed for the generistic aisle of dealership. The company is focused on addressing the biggest obstacle between electric vehicles and the mainstream: its cost. By choosing an existing platform, the Focus, and using technology developed by auto supplier Magna, Ford will save the expense associated with developing a unique design. The Ford Focus EV is targeted to have a range of 100 miles between charges, courtesy of a 23 kilowatt battery pack.